So it's nice to see persistent people still in the room. My talk will be about data assimilation. It's not really LiDAR focused, but LiDAR data estimates based on LiDAR data would definitely fit into these type of systems. So the background is that, as you all know, we have lots and lots of remote sensing data coming in. And especially not least in practical forestry, people are wondering how they should make use of all these data coming in. Should they care about it, or should they just go on as before, or should they do a LiDAR survey every 5 years and don't care about the Sentinel data, and so on. So could we do something else? And then data assimilation might be a possibility. I'm sure many of you know about this technique. It's applied a lot in other areas like meteorology, robotics, and so on. And we have a case in, well, basing remote sensing, all the remote sensing data coming in. We should really be able to do something similar in forest assessments. But for some reason, not so much is done so far. And it's a stepwise merger of their new information with existing updated information. You kind of add new information when it arrives to the existing information. In a simple overview is like this. So you have observations coming in, you have the updated old data, then you kind of squeeze it together, assimilate it together, you get a new updated state which you forecast, and then this will come here and we will have new data, and this continues forever. The theoretical potential is quite great. So you can achieve a lot with many observations. The standard deviation of data assimilation estimates would decrease, well, by 1 over the square root of k, with k being the number of DA steps. But then, of course, there are obstacles. There are obstacles like we have mixed time series, we have some good data, some bad data. We may make mistakes with putting too much weight on the bad data. We have to make accurate growth updates, which is not always simple, and which I will focus on now. There may often be correlated estimation errors. So we don't really get new information because we get the same errors back again when we apply the same sensor repeatedly. Some preliminary empirical studies have found that it's really difficult to realize the full, well, theoretical potential of data assimilation in practice. It may look like this. We can look at just one of these series. We start with a rather precise LiDAR-based estimate, then we add more imprecise estimates from other sources. So this would be the last observation, its accuracy, and this would be the assimilated time series. It's not really looking good. We don't improve a lot. So there seem to be many practical obstacles here to overcome. And we have quite a few studies of this kind, and they all tend to be a little bit disappointing. So in another study, correlated errors seems to be a major problem. In this study, it was found, and correlated errors can be of many different kinds. And one issue which has been touched upon in this conference several times is that we have, with regression-based estimates, we have this tendency towards the mean of the estimates we get, especially if the data are only weakly correlated with the dependent variable. This is nothing wrong. The regression model estimates the average value given the predictor variables, so it's perfectly fine. But when we have weakly correlated data, the kind of regression-based estimate will be shrunk towards the mean. And for data assimilation, this is a problem. We need the estimates to be unbiased at the unit level. So these observations, these updated states, they really need to be unbiased at the level where we make the assimilation, at the level of stands or plots. So, well, do we need unbiased or unbiased or unbiased estimators? If we just take the regression estimates, they're unbiased, conditional on the predictor variables. That is perfectly fine, but that is not good enough in data assimilation. And then we may look at them overall across the range of true values. Then on average, they're fine, unbiased, but that is not enough, sufficient for data assimilation. We really need estimate to be unbiased for each unit. I mean, conditional on the true values for each unit. So can we do something? Can we remove this tendency towards the mean, which is not really a problem with the model, because typically you would like the regression model to give you an unbiased estimate conditional on the predictor variables. But for data assimilation, that is not good enough. So can we remove this somehow? And we can actually. There is a technique called classical calibration, which is a means to remove this tendency towards the mean if you really would like to achieve unbiased estimates at the unit level, conditional on true values. So we have the estimation model like we typically apply. We plug in our data in the regression model, machine learning tool, deep learning, black box, I almost said, but there are so many techniques of this kind which you can apply, and they all tend to give you given the predictor variables, they report back to you something which is the average level for those predictor variables, which is fine. But then to do this classical calibration, you need to do this step as well. An error characterization model is fitted, where you characterize the estimate as modeled with field reference, the true value as a predictor variable. And then doing this, estimating this model, you can do the classical calibration, which is nothing new. If you go back in the literature, you will find hundreds of references to classical calibration. And this one suggests that a calibrated value can be obtained. You take the estimate minus the estimated parameter A divided by the estimated parameter B. And this can be shown that then if you do this, you will remove, what is this tendency towards the mean? So we're demonstrating this through simulation. One set of data, simulated data corresponding to LiDAR data, one set corresponding to Landsat data. And this is all fictitious then, so a little bit better than would be realized in practice. Looking at some preliminary results with the LiDAR, you don't really see the trend. They look good. There is no real tendency towards the mean, although there is a little which can hardly be seen, and the calibration is more or less the same. But with the Landsat, you have this huge tendency towards the mean, underestimating high true values, overestimating low true values. But after calibration, after the classical calibration, you have removed this trend at the expense of a larger variability around the line, a larger variance. If you apply that then to 10 data assimilation steps, you could see that with the LiDAR data, which were very good, assumed to be independent in this case, it doesn't really matter. The calibration didn't matter. It's more or less the same. But with the Landsat data, assumed to be Landsat data, is a huge difference. The calibrated starts at a higher level because we increase the variance through this classical calibration, but then since we remove the correlated errors, it will go down to a much lower level compared to using the uncalibrated estimates. And starting in this case with precise LiDAR-based estimates in both cases, and then adding, in this case, LiDAR-based estimates. It's the same figure as the other ones. It's not really interesting. But in this case, and this was what we have seen in many cases, that if you don't do the calibration, you will have this effect. You start with a precise value, and you add additional data uncalibrated, and you worsen the results. So adding new information makes our assimilated estimates worse, which is not what you would like to achieve. But with a calibrated, it goes down a little bit at least. So this is the same as I showed you before. You can see this kind of trend in this one, although even more pronounced, this upwards going trend. So it seems that this has the potential to improve the usefulness of data assimilation in practice, but it's still just a simulation study. Conclusions. So in data assimilation, then calibration is important for improved efficiency. These assimilation routines, they tend to be different in all fields of application, but in our case, then in the forestry case, this based on RS remote sensing data, this seems to be very important, as is also the case in other areas of application. But we will need to continue and struggle with other obstacles before we reach the target to have data assimilation as a strong implementable tool. So I guess that was it. Thank you.